Good afternoon, everyone. Um, we're all settled, yes? My name is Dean. I work at Google. I'm a software engineer, and I work on this thing called X-ray. So, show of hands, who among you have heard of X-ray? Wow, was not expecting that. Uh, so, well, maybe you already know what I'm going to talk about, but in the off chance that we're all here to learn. I'm going to talk about what we've been doing with X-ray at Google and what is already available out in the LVM project. So I have a few slides. It's going to go, and at any time, please bear with me. So a lot of people ask this question, so I want to get it out of the way. Why X-ray? So the first thing is, if you've ever tried to debug the latency of anything, you know it's hard. All the tools that are out there, they have their own special requirements, special niche. You have to hold it a certain way, and it will give you some data. And if you don't hold it some other way, it will also give you data, but it's not usually the data you want. So it's hard. And for systems that need to be fast, it gets harder. The existing solutions use sampling so that the overheads are low, right? And you can approximate the normal case. So statistics 101, if you take enough samples, you can take the average of stuff, right? Central limit theorem, everyone's happy with that. But if you want to debug the tail, that usually doesn't work, right? So it's okay to say, normally this thing takes some amount of time, but 1 out of 1,000 times, well, it's going to be slow. But if you're taking on thousands and thousands per second of operations, that's no way to debug your stuff. The other one is manual tracing is costly and error prone. If you've ever printf debugging, you know this is really hard and really hard to get right. And when you do get it right, it's sometimes like you've already spent so much time trying to manually trace your stuff that you forget what you were already trying to solve. And some require heavyweight support from the environment, from the operating system, from your tooling, and sometimes your users. So for example, if you're debugging a problem that's out there in production or in some customer's machine, it's going to be really hard to ask them to, okay, now you flip this flag, and then you get this file, and then you zip it an email. So it just can go so wrong so fast. And sometimes the environment you're going to deploy in doesn't have these features. Maybe older version of the kernel, or older version of some dependency library, or some tool it's just too hard. So the promise with X-ray is that first, we want to help make the cost lower and also the barrier to entry lower. So we use the compiler's help to do this. So for anything that uses LLVM, or mostly for C programs, we use the compiler to insert instrumentation at interesting points in a function. So suspend disbelief, right? We do this. The other one is we want to be able to turn it on and off dynamically so that you don't have to do some special tricks to get the data you want. You want to be able to just deploy, and when you want the traces, turn it on, turn it off, get the traces off the machine or from memory of the process, and then debug offline. And yes, basically debug offline. Because the last thing you want is run a debugger against something that's live and then slow it down, and now you have two problems, right? So we want to debug latency. We usually don't want to cause latency. So some constraints, we want it to be user controllable. So for example, we want to be able to turn off all the instrumentation and let the user decide that, hey, I actually don't want anything in this file to be instrumented, so there's a flag for that. And for example, if you only want certain functions in a file to be instrumented, we have attributes for that. It must work with llvm-xray, only because, well, it's easier to get it into LVM if it works with llvm-xray. Also, it allows us to do this for other languages that compile into llvm-xray. So you can use your imagination what those languages are. Use user pluggable architecture to support non-tracing use cases. So we're going to get to that later, but think about it as a framework. So X-ray, right? So let's talk about what X-ray is actually. X-ray is not one thing, and we're going to talk about all of them. So X-ray is compiler-inserted instrumentation. It is an instrumentation framework, so you can use it as well. X-ray is a tracing runtime, so there are parts of this that are part of your application's address space, and it can do funny things because it is part of your address space. We're going to talk about that too. And it's also a set of tools for analyzing traces. So step one, put your instrumentation in the binary. Step two, use the framework to engage with the instrumentation stuff. Then use the runtime to get traces, and then use the tools for analyzing. So in order, instrumentation, framework, runtime, tools. Yeah? Okay. So sleds and maps. So who among you have heard about knob sleds before? Knob sleds, usually not in the best of contexts, but I promise you we're doing something good here. So let's start with this. Oh, it's small, but imagine, right? Imagine you have a function foo that just calls printf hello X-ray, and then we have this attribute there that says always instrument this function. So this is C++11 attributes, and this is supported by Clang, so that when you pass it through the compiler using that magical flag in red, say -f X-ray -instrument, right? We are going to create assembly, yay. And in this assembly file, well, there's a lot of details here, but essentially we want to put an entry sled, which if you can read the assembler says ASCII stuff. Well, okay, so there's a limitation in LVM where you can't spell a 2-byte jump in x86, so we hack that by spelling out the exact bytes using ASCII, so the relaxation pass won't mess with it. And the next one is basically NOPs. It's an appropriately sized NOPs, exactly 9 bytes of NOPs. And then the exit sled has the return instruction. And after the return instruction, we have 10 bytes of sleds. So if we're doing math, 11 bytes for the entry, 11 bytes for the exit. It's going to be relevant later, I promise you. Cool. So if you're writing llvm-xray by hand, like some of you do, you can see that we have attributes for the function. And the attribute that's relevant is this function-instrument attribute. And you can say whether or not to always or never instrument. In this case, the example said always instrument that function. So when it lowered to llvm-xray, we have that attribute that says always instrument this function. Okay? So if you have a front end and you want to use X-ray, this is all you need to do. Cool. So let's talk about maps. We have a special section that we emit when we're lowering when X-ray is enabled that allows us to remember where these sleds are because reasons. So first, it's called the X-ray instar map, and there's no dot in the beginning because we want to be able to trick the linker into creating an array of these things by giving us a start and end symbol. So if you played with linkers enough times, you will learn that they will do special things for you. So that's our section. This is one that describes our entry sled. We use bytes to indicate, like bits to say this is an entry sled. So if you look at the first byte there that says byte 0, that indicates it's an entry sled. And the other one is an exit sled. And we have zeros for padding, essentially, future proofing. So we want to be able to put more stuff to this as we're going. In total, this is, if I do my math right, 32 bytes? Yeah, 32 bytes per entry in the map. So, okay, so now we have the instrumentation sleds in the entry and exit points, and we know how to get to them through this section. Okay? All right. We don't instrument everything, because as you can imagine, you might have functions that are really, really small that there's no point in putting instrumentation in them. It would just make them bigger and sometimes slower. Oddly enough, sometimes faster. But, you know, I didn't make this. I just work here. So only instrument machine functions with greater than or equal to 200. Don't worry about it. 200 is arbitrary. We did some experiments internally, and that's like, it doesn't grow the binary too much, but it's capturing enough functions that are interesting that it's worth instrumenting. If your function has a loop at the time when it's machine code, right, in the MC instruction passes, if you still have loops there, we will instrument it for you. And functions can be always or never instrumented. You can use a special case list, similar to how the sanitizers allow you to do blacklists. So we have a couple of flags in Clang that allow you to specify, say, always instrument all the functions in this directory, or never instrument like anything in this special directory, because you have hand-tuned kernels in there and you don't want Clang messing with it. All right, so we talked about the instrumentation that the compiler inserts. Now we're going to talk about the framework that you can play with when you're X-ray instrumenting. So we come out first with a few constraints. First of these constraints is we want to be able to patch and unpatch the instrumentation sleds at runtime without stopping your application. So no ptrace that will stop your functions and all your stuff, right? We are going to do this, like, hopefully correctly. We also want to be able to install handlers atomically, so that you can say, when these entry events and exit events are encountered, as soon as this handler has been installed, all the threads should be able to see this, and then instrumentation is on. And you want to be able to also turn it off atomically. So there's some interesting memory model tricks we need to play with that. We also want to only patch and unpatch instrumentation points, because the last thing we want is to let arbitrary stuff happen at any point of your program instead of just the instrumentation points. We're not in that business. Okay, so remember this thing. We have an instrumentation map, right? So now at runtime, we have this map that tells us where the sleds are. And so we have this simple algorithm that goes, for each entry in that sled, if it's an entry sled, we want to change it so that we put a function ID in a scratch register. And we want to call an entry trampoline. So I'm going to hand wave the entry trampoline what it does. Just assume it does something non-nefarious. The second one is, if it's an exit sled, we want to change it to put the function ID in a scratch register and then jump to an exit trampoline. So you can imagine that exit trampoline has a return somewhere, right? Okay. So let's look at some code. Remember our favorite foo function that, oh, wait, actually, foo function sounds like a really good band name. It's like the foo something or something. Anyway, so when you disassemble foo before patching, you will see the jump across. It's a 2-byte jump to 11, which is spelled as jump plus 9. And then you have the nops that are 9 bytes. And so basically, this is the beginning of your function, right? Function is called, execution gets to the jump, skips a few bytes, we're fine, right? Okay, and the exit at the bottom looks like return and then some nops, right? So this is fine. Now when we patch, it turns into move number. That number is computed at runtime for a function ID and puts it in a scratch register, calls the trampoline for entry. And at the end, you see you have a move, the same number, the function ID, into scratch register, and then jump to the exit trampoline. Yeah? So, sounds simple, right? This is all X-ray does, for x86 at least, 64. So I didn't show you the slide that says how complicated this is in PowerPC, and how do you do this in ARM, and different memory models, et cetera, But this is nice and concise for x86. Okay. Here's the trick. How do you do this when you have multiple threads? Well, the answer is you do it very carefully. So remember, we want our jump across bytes to turn into a move and a call, right? So if we're doing some math here, the move instruction is 5 bytes or 6 bytes, and the call is 5 bytes, so 11. So it fits nicely into that 11-byte sled we have, right? Okay. So this is the before, right? So we want the move call, and we want to change the jump nops, okay? So first, right? Are you ready? I'm never ready for this. So the jump has to be 2-byte aligned. Anybody know where this is going? We're going to play some atomic games here, okay? So 2-byte aligned. Why? I'm going to say why later, but we want to write in reverse. So write the 5-byte first, write the call, and then you want to do a partial write of the move instruction. So you write the next 4 bytes, right, over the part of the nops. And then finally, you want to overwrite the jump to be the first 2 bytes of the move instruction. And you want to do it in this order, because any other order is going to be weird and error-prone. So because the cache line is evenly sized, you want the jump to be aligned evenly so that the 2-byte jumps never straddle 2 cache lines, right? And so the writes that happen before it may be on a different cache line, and essentially you need some sort of barrier to do it right. So those have to commit first, and then you do your 2-byte write over the jump. So, yeah. Told you it was simple. Now, when we're unpatching, it's much simpler. We just write the jumps and the ret, because we can't be sure that there are no other threads that are in the middle of those bytes. Okay? And this is x86. Like, I'll leave the imagination of other platforms to you guys. Okay. So what do you do when you want to actually intercept these events? There are functions in the compiler RT part of X-ray that allows you to install function pointers that get called by the trampolines when these entry and exit events come in. We also have a mechanism for custom event logging. And so custom event logging is a feature you'd want to use if you want to delineate phases in your function, for example, or you want to associate some identifier to a thread of execution. So if you have RPCs, you could use the RPC ID or some notion of such as a phase indicator that says I started here and then I ended here, right? And we can also get the first argument of functions if you use the attribute that we provide, and that's useful for getting the address of objects. So if you want to get the address of an object where you call a member function that you instrument, say for example you're doing locks, you want to get the address of a mutex and be able to offline figure out which mutex was causing your latency, then you can do that. Cool. So talked about the framework, so you can install your handlers, and the patching and unpatching are done for you in the LVM compiler RT aspect of X-ray. So now we talk about the runtime. So we have a default implementation, or a couple of default implementations, where we're able to get the entry and exit events using your platform or your OS-specific high-resolution time mechanism. In x86, we use RDTSCP. So we get the CPU ID and the TSC. So we can reconstruct your call stack offline just using the log. So the naive mode or basic mode gets all the events, absolutely all the events. We will write everything. We are not going to filter anything. If you suddenly get like a 38 gig trace of Clang, we warned you. Flight data recorder mode, on the other hand, is something you can turn on and off. It will do basic filtering so that it doesn't write too big a trace, and you can control the amount of memory it uses in its circular buffers in memory. So imagine you have a way of intercepting entry and exits, and you can get the timestamps at entry and exit for a function. And you can do this for all the functions that are X-ray instrumented in your binary, right? And then you can collect these traces as files. So the default implementation we write out files to your file system, right? FDR mode can be used without using files, but yes. So they both cover the same events. We only so when we write out these files have different formats, but the LVM tooling that deals with the X-ray traces actually can handle both of them. And basic mode is great for command line tools like Clang, like LLC, like any of your lovely command line tools. And it can generate a ton of data. So yesterday when I was doing this, I did a fully instrumented build of Clang, and I compiled the Hello World C++ program, and 38 gigs later, I have a trace. So your mileage may vary. FDR mode is great for long-running applications. So imagine a web server or an RPC service, right, that you want to be able to dynamically get some traces for at runtime because there's a latency event. This is the one you want. All right, here we go. So I have some time. Let's go through some basic mode demos. I won't actually be doing demos because I learned from the best. So here's some code, right? This is a contrived example. We always instrument foo, which basically says hello X-ray, bar, which takes the first argument, and we have that attribute that allows you to get the first argument. And then we also fully instrument main. We always instrument main, so we want to get that. All it's doing is calling foo and bar, right? Easy enough. So when we build with this, right, we just say dash f X-ray instrument, and we run it. Nothing special. So by default, X-ray instrumentation is off, right? So we do link in the binary that you require, but when you run it, it doesn't always trace right away. So you shouldn't be able to tell whether you're using an X-ray instrumented build when you're just running something you just built. If you wanted to actually get the trace, we use environment variables for that. So there's a lot of letters on the screen, but basically you want to say patch before main starts, and then use the naive log mode, and then run the function, or run the binary. And here we get, say, yep, thread ID X-ray log, it's in this file, right? So now as soon as your binary exits, you have a file that you can start analyzing. We can do that later. So FDR mode. So how different is FDR mode? Well, it's a slightly different. There's more code in this example. But basically what we want is the first function will either take 10 microseconds or 100 microseconds. Okay? It's flipping a coin, not the most secure way of flipping the coin. Don't do that at home. But it's good enough. And foo will basically call bar in a tight loop and look at the global to figure out whether it's done. Okay, quick. Remember, no. There's more, actually, because we need the main function. Okay, we're good? Yeah? All right, so the main function looks like this. Line number 44, we actually set up the default options for FDR mode. We patch before we install the handlers. Then we install the handlers. So line number 46. Yep, 46 is where we initialize the logging implementation. And then we wait. And the way we wait is, in this example, we take input from standard in. But before we do that, we run the threads. In the background, we have two threads that are calling foo. Yeah? That is in line 39 and 40. So we have two threads that are flipping coins and then waiting to be either 10 microseconds or 100 microseconds. Yeah? Okay. And then when we get input from the command line, we then finalize the log, and then that stops all the instrumentation handlers from instrumenting. Then we flush the log and unpatch the binary, just to keep things sanitary. All right, so when you run this, you need to turn on FDR mode. You need to turn off naive log, and you don't need to patch pre-main because we're actively patching in the main thread. All right, okay. So environment variables are set. We run it. We enter something in the command line, and then that stops the process, right? Okay. We're going to analyze that later. Okay, cool. So far, yeah? I have very few minutes left. So let's talk about the tools. So now you have traces. What can you do with these traces? All the code for the tools come to this llvm-xray binary. It's in your LVM checkout. It's in the tools directory, and you can use this today, top of tree LVM. The libraries that the tools use are there, so you can build upon the trace loading and the instrumentation sled in your own tools if you want to. And you can also add subcommands to the llvm-xray tool, and we're going to go through a few of those here. So first thing we want to do is we want to sometimes get which functions are actually instrumented in our binaries. So we have a tool called llvm-xtract. So you can extract the instrumentation map from your binary. It outputs it in beautiful YAML because we already have a YAML library and we should just use it. We can also, if you have debugging symbols, we can actually symbolize and you can associate which functions or which function IDs, and you can get the address of the sled and the address of the function. So you can do interesting things with this. There's a tool called convert. So remember our trace files earlier. You can take one of those and then convert them into YAML. Because maybe you have tools that deal with YAML and you might have scripts that you want to write and stuff. But it's possible. So here we have it. So it gives you the timestamp counter, what kind of event it was, and for which function ID, on which thread, and on which CPU. So you can now imagine what you can do with this data offline, right? So this works with the naive mode or basic mode log. We also support the FDR mode log. And this one has more events. So I only show the top 20 lines because there's too many lines, right? Yep. And we can also generate a graph of this. So this is the graph of the naive mode log. Basically, we're showing how many seconds were spent in which function, and we color code that to figure out which function actually contributes more. So in this case, it looks like foo was taking more time than bar. This is the FDR mode log, which isn't very helpful because we have one function being called in a tight loop in 2 threads. But it shows up as this, and you can say, well, it was called 8,846 times between the time it started and I entered stop in the command line, right? So we can also account the functions. So here we have a distribution. It's not easily seen, but this is for the naive mode. So we can see foo was called once, and the minimum was 36 microseconds. Maximum was 36 microseconds. If you recall, foo was printing hello X-ray. So you can imagine, well, it took 36 microseconds to do that? Yeah, actually, some parts of the standard library are slow. Bar the same, so it's quicker because it didn't need to do the initial setup of your IO streams library. And main took like the combined time plus a few more things. And if we account for the FDR mode, remember how bar was flipping a coin and figuring out whether to be 10 microseconds or 100? Yeah, the distribution shows that the minimum is 16 microseconds, the median is 114 microseconds, and the maximum was 192 microseconds. So your nanosleep isn't always, accurate, right? And so we have 8,800 recordings of this function in the time that we were tracing. Cool. So the other thing we can do is create pretty graphs. So we have a tool called Stack, which will do the accounting and figure out which stack was contributing the most time. So if you imagine your program pushing things on the stack for function calls and then popping, right? You want to be able to figure out which stacks were contributing the most time. So that flame graph tool is a tool that is available open source, released by Brendan Gregg. And so we're basically just going to use that. So I prepared some because I learned from the best. Yeah. So this is an example of the Yep. So remember our naive mode example? We had main call foo and then bar. It shows that, well, most of the time was spent in main, not surprisingly enough. And then you see foo, right? And so which thread was doing that? Okay. So I have another example of this where this is the FDR mode log, which showed, well, we had 2 threads. And the first thread was calling bar. It had 50% of the contributions. The second thread was doing similar, I guess. Now we consolidate them and see that, well, okay, all our functions are bar. So I also prepared one for Clang. So I built Clang with X-ray instrumentation. I only instrumented functions that had 75 instructions because if I used one instruction, it just 38 gigs, and my machine didn't have enough memory to deal with that. But so 75 instructions threshold and ran it on hello world. So this is not the full graph. So that's a really deep, 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 deep stack. So yeah, can anybody guess what Clang is doing? So for Hello World, it was mostly parsing the AST, parsing a top-level declaration, external declaration, and then templates. That one, parse, template, declaration, or spec. And then there are flames that come out of that, because when you do that, yeah. So there's more deepness. So this SVG, this is an SVG, right? If you click on one of these, it should show. And yeah, so if you like flame graphs, you can build flame graphs with llvm-xray, the tool. Okay, so I have very little minutes, but let's go through a few of the slides some more, just to be complete. Right, so recap. X-ray is instrumentation. It is a framework you can use. It has a runtime that allows you to do two different things but cover the same kinds of events. And we also have tools. So this is available in Linux. In these platforms, not the best slide ever, but x86-64 has all the features. That's our primary platform we develop on. And there's PowerPC, ARM, ARM64, and most of the variants of MIPS. And if you want to use this for your front end, back end, or OS, we support and would like contributions. So we are looking at how would this work in other OSs, other platforms. And we also are looking into more visualization of the data and more analysis. So you can use this today, top of tree of Clang, compiler RT, and LVM. Thank you very much.
Thank you, Dean, and we are looking for questions. Do you have possibility for remote profiling?
Remote profiling. So technically, yes. So if, for example, if you had your own RPC system, or if you're using one of the RPC systems out there, you could imagine implementing the FDR mode handlers to patch, gather the data, and also stream the data out. So this doesn't require that you have the binary running on your machine. So that answer this question? Yeah. Cool.
How do you allocate the scratch register for the function ID?
How do we allocate the scratch register for the function ID? We just use it. Right. So x86-64 says that that register is not guaranteed to be preserved across function calls. So before you enter the function, it could be reset to anything. So we're exploiting that. At the same time, because it's not preserved across exits, we're basically using it as a real scratch register.
Right. So on ARM, you have volatile and non-volatile. The thing is, on ARM, all the volatile registers are used for argument passing. So you cannot use any of this. You have R12 maybe.
Yep. So the ARM implementation was not done by me, but it does something similar. So what it does is, I think it stashes one of the registers first, uses it, and then unstashes it afterwards. But the patches are up there. It's upstream. If you think it's doing the wrong thing, let's fix it, yeah?
So the thing I'm trying to get to, do you have to recompile everything, or can you link with things that are compiled without instrumentation?
So the answer to whether you can link in something that has instrumentation versus one that doesn't is yes. Now, whether you have special calling conventions that do funny things with the R10Ds, for example, in x86, then you're on your own. Yeah.
Any detectable runtime overhead.
Any detectable runtime overhead. So that's a good question. So first thing I want to mention is we have the benchmarks in the test suite as well. So you can verify this on your own. But if you just built with X-ray, for most of the things we measure, we can't tell. Now, I recommend you benchmark both micro benchmarks and macro benchmarks. And I'm talking about macro and some micro benchmarks. There are some micro benchmarks that are very sensitive to layout. And because we're adding bytes here and there, we can make things slower. And in some of the cases, we do make things faster. So if X-ray makes your stuff faster, I recommend you use it. But yeah, so in general, it's very minute and we can't really tell. Yeah.
On one of your slides, you showed you have special sections.
Yep.
And you have some dependency on a linker. My question is, what kind of linker? So,
right.
GNU linker or L?
Right. Yes. So the question is, will the tricks with the special section work?
Well, in ARM we have own linker.
Right.
And we have another mechanism, scatter files instead of GNU linker files.
Mm-hmm. So the ones we've tested with are Gold and LLD and binutils, the BFD linker. So they seem to work.
Okay.
With those linkers. So if your linkers behave similarly, then yes.
Who knows? Another question.
Yep.
Most of our configurations are bare metal, so we don't have operation system at all. And I see this really great tool to do profiling of bare metal applications. Is the design of X-ray aware about this model, or its operation system is a major requirement?
Right. So the only requirement we have from Linux are two things. One is mprotect, so that we can overwrite the text section while it's running. And the other one is mmap, so we can allocate the memory for the buffers. I'm sure in an embedded environment, you don't need either of those. And so we can probably implement something in compiler RT for your environment where basically it just works, right?
Does anyone use X-ray in the embedded world? Any use cases? It's
I haven't heard
out of curiosity.
Right, I haven't heard of any yet.
So there is opportunity.
Yes, there's an opportunity to make this happen in any platform. So yes.
Okay, thank you.
I think we have a question back there.
Are there any plans to have this work with any other calling convention other than the C calling convention?
So,
Because right
actually,
now you hard code D10.
yeah, so that calling convention assumes the sys ABI, sys64, yeah. We have compiled stuff that use the C calling convention, it works. I'm not sure whether, so if your calling convention uses R10D, probably not.
Okay.
But we can probably work around that too.
Okay, thanks.
Think that's it? Oh, wait, yes, Greg.
So I actually have kind of a use case, depending on your definition of embedded. The Linux kernel open codes something very similar for its tracing subsystem. The problem is it only works with GCC because it depends on a really awful hack called asmgoto that Clang is probably not going to support. And so the actual rewriting part where you basically do what the Linux kernel calls static branching is basically what we would need. Is that separable out from the rest of X-ray? Like, can we take that without taking the rest of the tracing infrastructure, which the kernel already has?
I suspect so, yes. It's not special what we're doing. We're basically hard coding the patching in compiler RT. And so it's a function call that says if you're able to synthesize this instrumentation map for the kernel, then yes, you can port that easily. The other option is if, say, for example, we wanted to build the Linux kernel with X-ray instrumentation, we'd have to invent like how to embed compiler RT parts of X-ray. But yeah, if the kernel already has it, then
Well, we know how to do that, which is you re-implement them inside the kernel.
yes. So, yep.
It seemed to me like you ought to be able to use the return address that the call instruction pushes just by looking at the top of the stack instead of using a scratch register to pass in like a function ID.
Yes and no. So sometimes, there's sometimes when you actually don't push the return address on the stack. So when you're using special, what was it called, the calling convention, where you can just use the red zone of the stack. So we can't rely on that being always there. This also, so the function ID serves two purposes. One is to be able to decouple the addresses of the functions to the identification of a function, and the other one is so that even if the return address is up there, we cannot assume that you will have a local return anyway. So you might have a set jump, long jump in the middle, and while your trace will be weird, X-ray can still deal with it, right? And so there have been variations of how to figure out how not to use the scratch register before, and it turns out like none of them are easy, and we settled on this solution for now.
Yeah, think about tail calls, for example.
I think we're good. Thank you very much, everyone, and yeah.